Hey everybody, so I'm going to go through and do an example with you for how to do our statistical process control charts. Now these are really important because it helps us determine whether or not some of the variation we see in our process, if it's a normal cause or if it's an assignable cause, meaning that a piece of equipment needs to be recalibrated, or maybe there's somebody new who's working the job that needs additional training. By tracking the data over time, by taking samples, and by establishing upper and lower control limits, we can actually statistically determine whether or not our process is in control or if something has changed. And this is really important too, as we consider for a lot of companies that track their operational data. We don't want to be making comparisons, say our performance this month as compared to last month. What we want to do is we want to make sure that we're tracking this data over time, because there's always going to be some fluctuation in the data, and we want to know whether or not we're still kind of in that normal range of seeing some of that variation, or whether or not something significant has happened. So this example that I'm going to walk through today, I've included a solved PDF on Blackboard as well. So this is a simple example. I'm taking this from the 60 Minutes YouTube video that was posted as well, regarding Cheryl Eckert, who is the director of quality for GlaxoSmithKline, who went and investigated their Cedra plant in Puerto Rico and found a number of issues with their production process. So we're going to walk through basically the approach that you could take, and in this case we're going to assume that we're just looking at the drug Avandia, and we want to be looking at we want to be taking samples to see what the weight is of the pills, to make sure that the weights are correct and we're not seeing too much variation. So here we're going to want to see an average of about 10 milligrams for all of the pills. So what we do is a part of the sampling process whenever you're doing quality control is you want to go out periodically. So in this case we're going to say that we take 10 samples, so we can just assume that, you know, over the course of 10 hours during the day, maybe going out to the line once each day, we're going to take a sample of 6 pills. Now it's really important that we differentiate this. Our N, for the purposes of creating our statistical process control charts, is going to be 6. N is the number of samples that you're taking at any given time, not how frequently or how many total samples you have, you know, throughout the course of the day or over time, because we're going to assume that we're going to continue to take samples over time. But what's really important is how many samples you're taking off the line at any given time. In this case, we're going to take 6 pills every hour when we go out to the line. We're going to sample 6 pills, so our N is going to be 6. So what we do here is we've got a sample, we've got 10 different times that we've taken, we've gone out and taken a sample throughout the course of the day. And what we have here is the sample mean. So the sample mean of all of our 6 samples for the first time we went out and took the batch off the line is 10.2. And the range is just the difference between the highest value and the lowest value in that sample of 6 that was taken off the line. So for every hour that we go back out, we're going to take the average of the 6 samples, and we're also going to take the range. So these are really important because this helps us determine what our X bar is and our R bar. So the way we calculate this is, in order to get our X bar value, we're going to sum all of the values that we have here. So in this case, that is going to give us a value of 104.2. So if you added these all up here, 104.2, and then we're just going to divide by the total samples that we took off the line, which is 10, and that's going to give us our average here of X bar, and that's going to give us 10.42 milligrams. Right, so that is basically the average of all of the averages, which is why it's called X bar. We're going to do the same thing for the range. So here we're just going to sum up these values. This is going to equal 98. We're going to divide by 10 here, and that's going to give us an R bar, an average range of 0.98. Oops, I'm sorry, this should be 0.98, or I'm sorry, 9.8, and this is going to be 0.98 milligrams. Okay, so we have our X bar and we have our R bar value. So the next thing we want to do is we want to evaluate 2 things. We want to look at the central tendency of the data. So is the data with some level of confidence around that 10 milligrams. And also we're interested in the variation. So are we seeing a lot of variation in terms of the data? So the two charts that we use to do this are something called mean and range charts. So really what the X bar chart does is it's checking the central tendency of the data. So this is looking for the central tendency. And our R chart, that range chart, is going to tell us, that's going to tell us basically how much variation we have in our process. So here's two examples to talk through what that might look like. So if we have, let's see that every time we take a sample of 6 off of our production line, we're seeing that the data or the values are pretty normally distributed, right? There's a normal amount of variation or consistent amount of variation between our samples, but we see that the values are starting to shift upward. But again, the range is consistent in this case. When we calculate our X bar and our R bar charts, that would correspond to us seeing values in our R bar charts. Once we calculate our upper and lower control limits, we're going to start to see these values shift up, right? So that's going to indicate at this point that our process is out of control, because one of our values is outside of the upper control limit in this case. But from our range standpoint, everything looks good. It's okay. So there's no change. There is a change in our central tendency, but there's no change in the variation of the data. We always use these two charts together. So in this case, again, we would indicate that this process is out of control because one of our values is outside of the X bar chart upper control limit. So in the event where maybe the central tendency of the data is good, maybe in this case for our Avandia example, all of our values have a mean of about 10 milligrams. But one of the other issues we could see is that while originally there was little variation in the data in the sample, maybe over time we're starting to see that there's more variation, or our range in our upper and lower values for the samples that we're taking off the line are greater. So when we see this dispersion increase, that's going to also present a problem. That's going to say that maybe there's a piece of equipment that needs to be recalibrated to make sure that we're basically the variation in the sample is going to stay the same. So again, when we're doing our X bar and our R bar chart, in this case, everything looks good. All of the values are falling within the upper and lower control limits. But in this case, we start to see an increase in the dispersion of the data. And here, we see a value outside of the upper control limit of our R bar chart, and that is going to tell us that this process is out of control. Okay, so this is basically what we're looking at with statistical process control, is we're actually taking data over time, taking samples, and starting to see, if we get a value that is outside of the X bar upper or lower control limit, that's going to tell us that the central tendency of the data is shifting. So in the case when we go to look at Anheuser-Busch, one of the key parts in their production process that they test for is fill levels on the bottle line. So every bottle has to have 12 ounces, right? As they're tracking the data, if they start to see that fill level was getting outside of the upper control limit, that would indicate that there is a problem that needs to be addressed. Likewise, if we're starting to see that, let's say on the bottle line at Anheuser-Busch, that all of the values fall within 11.9 to 12.1 ounces, that's fine. But if we start to see that range gets bigger, again, that is going to be another indication that our process is out of control and we need to go back and figure out what's going on. And the key here, and this will be on the exam, is again, statistical process control. Not only will I ask you to calculate some of these and determine whether or not the process is out of control, the key difference is we are trying to differentiate some of the normal causes of variation, the things that we see, the normal variation that we would see in any process, versus an assignable cause that needs to be addressed and fixed. Okay, so getting back to our example, so in this case where we're looking at Avandia and we're taking samples off the line, we've calculated our X bar value, which is 10.42. We've calculated our R bar value, which is 0.98 milligrams based on the information that we have. Now we can calculate the upper and lower control limits for both our X bar and our R bar charts. And again, the X bar is going to tell us about the central tendency of the data, and our R bar charts are going to tell us about the variation or the spread. Okay, so our formula for our upper control limit for our X bar chart is going to be X bar bar plus A2 times R bar. And the lower control limit is going to be X bar bar minus A2 all multiplied by R bar. Now this A2 value is a constant, and the table to find these constants is located in your text. The way this works is that we have to determine what our sample size is, and this is very important. Again, it's not the total number of times that you went out to the line, but it's how many samples were in each grab. And in this case, we had our N is 6, right? There are 6 pills that we're taking with each sample. So our A2 value for calculating the X bar chart, upper and lower control limit, is going to be 4.83. So we're going to plug that back in here. So again, based on an N of 6, our A2 value is going to be 0.483. So when we calculate the upper control limit, our X bar bar value again here is 10.42 plus 0.483, all multiplied by our R bar value, which is 0.98. And that is going to give us a total, our upper control limit is going to be 10.89 milligrams. And our lower control limit is going to be 10.42 minus 0.483, all times 0.98, and that's going to be 9.95 milligrams. Okay? Now we're going to do the exact same process for the R bar chart. So there are different formulas here though. So our upper control limit for understanding the spread or variation in the data is going to be D4, which is another constant from our table, all multiplied by R bar. The lower control limit is going to be D3, all multiplied by R bar. And again, we need to come back to our control chart factors table. Again, in this case, our N is 6, right? We're taking 6 pills off the line. So here, our value for D4 is going to be 2.004. And the D3 value that we're going to use with an N of 6 is going to be 0. Okay, so we're going to plug these back in to our equations. So D4 is going to be 2.004, all multiplied by our range, which is 0.98, which is going to give us 1.96 for our upper control limit on our R bar chart. And our lower control limit is going to be that constant. In this case, for an N of 6 is 0, all multiplied by 0.98 is going to be 0. Once we have that information, we can actually graph our upper and lower control limits. I've done this in advance just to show you what it looks like, but make sure that you can go through and graph this data as well so that you can determine whether or not a process is in control or out of control based on the data. So in this case, so if we take a look here up at the top, this is our X bar chart. And so the central line is going to be X bar bar, which in this case is, again, 10.42. And so our upper control limit, again, for the X bar chart is going to be 10.89, so that's right up here. And our lower control limit is 9.95. And then we can basically take the values from the data. So from sample 1, the mean was 10.2. So we're going to graph that for sample 1. That value was 10.2. And we go through and do that for all of the means that we took with each sample. And what we can see here is that we have several points up here, down here, back up, down, which would indicate to us that there is a significant amount of movement in the central tendency of the data, or the weight of the pills in this case. That would indicate that our process is certainly out of control, and we need to try to understand whether it's an equipment issue, whether there's something with the production process or with training that's causing this much variation in the data. In this case, though, if we look at the R bar chart, in terms of the variation or the spread in the data, it looks pretty good. So what we're seeing is that every time we go and take a sample, the values are pretty close to one another. but we're seeing a wide variety of shifting, again, in that central tendency. So even though the R-bar values are falling within the control limits, here in this case, certainly we have a number of points that are falling out of both the upper and lower control limits on our X-bar chart, which would indicate that this process is out of control. Again, we will see this on exam number 2 as well as the homework. If you have any questions, please feel free to reach out to me at any point.